Okay, good day, grade 10s. I trust that you are well. Today we are going to look at some revision with regards to algebraic expressions, right? So this is quick grade 10 revision. And remember, this lesson does not cover all the content we have done for the term. It is very important that you go through the topics done in class. This is just a revision highlighting some of the important areas. So please note this video is very limited. So it's very important that you go through the exercises in your textbook and what we have done in class. Now that being said, let's jump into the first exercise. Now, when you look at rational and irrational numbers, the first very important point to mention is that if a number is either a rational or an irrational number, then it is part of the real number system. It is a real number. So a real number is defined as a number that is either rational or irrational. But this begs the question, what is a rational number and what is an irrational number? A rational number is any number that can be expressed as a fraction in the form of a over b, where a is an integer. So what is an integer? It's your positive and negative whole numbers. And of course, so 0, 1, 2, 3, 4, 5, 6, 7, all the way to infinity, negative 1, negative 2, negative 3, negative 4, all the way to infinity. Does it include any fractions in the sense that it is a part of a whole? No, it does not, right? So where a is the element of integers and b is the element of integers, but b cannot be equal to 0. Now, why can b not be equal to 0? Because if b is equal to 0, then I have a over b, which is undefined. Now, an irrational number is basically the opposite. It is a number that cannot be expressed as a fraction in the form of a over b, again, where a is the element of integers, b is the element of integers, and of course b cannot be equal to 0. So that's the restriction. Now, this is a very important question. A rational number can be expressed as a fraction. So for example, a half is a rational number. Why? Because 1 is an integer over 2, which is also an integer. So it's an integer over an integer. But of course, we can express half as a decimal, 0.5. And 0.5 is a rational number. Why? Because we can express that as a fraction. Now, if I look at an irrational number, the most common irrational number is pi. Why? Because I cannot express pi as a fraction. It is the ratio of the circumference of the circle to the diameter of the circle, and it's always 3.1415 and so forth and so on, right? And it reaches to infinity. Now, one could argue, what about pi over 1? But remember, the definition of a rational number is that it has to be an integer over an integer, and pi, which is in the numerator, is not an integer. So therefore, it is regarded as an irrational number. For example, an irrational number could be the square root of 2 or the square root of 3. So you get the point. There's infinite rational numbers and there's infinite irrational numbers. Okay. That being said, what about a recurring decimal? A recurring decimal, right? As the name suggests, this is a non-terminating decimal. That means the decimals do not end. Now, pi is an example of a number with the decimals that do not end, but this is a reoccurring decimal, meaning that it follows some sort of pattern. For example, let's say I ask you to write 0.134 and there's a dot on the 2 and there's a dot on the 4 as a rational number, because a reoccurring decimal is actually a rational number, and we can prove it. We can write this number as a fraction. So first things first, what do we mean by 0.234 and the two dots here? You can also write this as 0.234 and there's a dot on the 2, dot on the 4, and there's a line that goes in between. This actually means that the digits 2, 3, 4 is being reoccurred. It's following some sort of pattern. So this is 0.234 2, 3, 4, 2, 3, 4, 2, 3, 4, and you get the point. So this can continue to infinity. It does not end, right? But we want to write this as a fraction. So step number one, I'm going to say let 0.234, and so forth be equal to x, right? So x is equal to 0.234 reoccurring, right? Now that I can see how many digits are being repeated, right? Because I want the remaining decimals to be 234, 234, 234, so that I can get rid of it, right? There are 3 digits that are being repeated. So I want to move the decimal comma 1, 2, 3 places to the right. And in order to do that, I need to multiply this decimal by 10 raised to the power of 3, because when you multiply it by 10 raised to the power of 3, the decimal comma moves 3 places to the right. By the way, on a side note, if I had to multiply this decimal number by 3 raised to the power of -3, then it moves 3 places to the left. So you get the point, right? The decimal comma will move depending on base 10 raised to some exponent. And that number by the exponent tells me how many places to move 10, right? So back to this question, what I'm going to do is, let's multiply the original equation, right, by 1,000. So I'm going to multiply the left-hand side by 1,000. So 1,000 times x is 1,000x. I'm going to multiply the right-hand side by 1,000. So when I multiply the right-hand side by 1,000, decimal comma is going to move 1, 2, 3 places to the right. So what do I have? 234.234 reoccurring. Okay, now I have the first original equation, which is x is equal to 0.234234 reoccurring, and I have a second equation, which is 1000x is equal to 234.234234 reoccurring. So I'm going to subtract these two equations together. Let's start with the bigger equation first. So I'm going to say 10,000, sorry, not 10,000, 1,000x. So this is 1,000x is equal to 234.234 reoccurring. So 1,000x minus x. Remember, what is the coefficient of this number? It's -1, right? It's equal to 234.234 reoccurring minus 0.234 reoccurring. So what I'm going to do is I'm going to subtract the decimals, right? And the units will subtract with the units. So you can see that 4 is going to be subtracted, or rather 0 is going to be subtracted from 4. But what happens to the decimals? The decimals, although it's going to infinity, they should all cancel out with each other. For example, this 4 and this 4 give you 0, 3 minus 3 gives you 0, 2 minus 2 gives you 0, and you get the point, right? So they all basically cancel out each other to give you 0. So it's 0.0. So what do I have? On the left hand side, I have 10,000. Sorry, I keep on saying 10,000. 1,000x minus 1x, which gives you, what is that? 999x is equal to 234. Now I just simply solve this equation. I divide both sides by 9,999. I divide this side by 999. The 999s will divide off. X is equal to, now you just need to simplify this fraction. I recommend just take your calculator and type in 234 divided by 999. And what does that simplify to? 26 over 111. Now it's very important, very, very important to simplify your final answer. Very, very important. Okay, so if you want, you can test this out. Let's take our calculator, right? And the original number was 0.234234234. So what I'm going to do is I'm going to take my calculator and I'm going to type in as many 234s as possible. 234, 234, 234, 234, as many as my hand can allow me to type, right? Because of course it's infinite. It's impossible to type to infinity. And what does it give me? Your calculator will approximate it to the number, which is 26 over 111. And by the way, what is 26? 26 is an integer, and it's being divided by 111, which is also an integer, thus proving that this number is in fact a rational number. Very, very interesting. Okay. Now we're going to move on to simplification. Or before we go on to simplification, sorry, let's represent numbers on a number line, which is also very, very interesting. Okay, so let's minimize this. Okay, so by the way, right, there's two ways we can represent a number on a number line. Right, so that's what we are going to look at now, representing numbers on a number line. Okay, so there's two ways we can represent a number on a number line. First, a number, the notation of the number could be in set Bowler's notation. Now, set Bowler's notation involves a set of x values that is represented as an inequality. We know what an inequality is. It's not equal, so it's less than, could be greater than, it could be less than or equal to. That means that value could also possibly be equal to that amount. And the last one, we have greater than or equal to, right? And we also have something called interval notation. Interval notation, right? Which involves brackets, either square brackets, which means including that amount, or round brackets, which means excluding that amount. But we will look at an example of that when we get to it, right? But firstly, let's start off with set Bowler's notation. Right, let's start off with set Bowler's notation. Okay, very, very interesting stuff. Now, let's say we are required to represent, right? You read this as x is a set of x lies between -1, but remember, okay, is x equal to -1? No, it is not. Why? Because there's no equal to sign here. If there was an equal to sign here, that means x could possibly be -1 as well. But in this case, it is not. And we have something that looks like this. Now, this means that x lies between -1, but it's not equal to -1, and 2, but it is also equal to 2. That means it could be equal to 2 as well. And it goes on to say x is the element of integers. Now, I explained to you what integers are. It's basically all your whole numbers, like 0, 1, 2, 3, all the way to infinity. All your whole numbers and the negative versions of those whole numbers. So if you have 1, there's -1, -2, -3. By the way, is -1/2 an integer? No, because it is a fraction, a part of a whole. Now let's represent our example onto the number line. Right? So of course you have a pencil and ruler, and I'm pretty sure your work will be much more neater than mine. So what I'm going to do is I'm going to first draw a number line. I have 0, 1, 2, 3, 4, and to the left of 0, those are my negative values, -1, -2, -3. Now x lies between -1 and including 2. Now many learners are so tempted to draw that bar above. But just remember one thing, right? Just remember something very, very important. Can we include fractions? We cannot. So if I do this, it's incorrect. Why? Because you can include 0.5, but 0.5 is not an integer, so I cannot do that. If x was the element of real, if they told me that x was an element of real, then of course I can say that yes, x lies between -1 and 2, and it includes 2, so I'm going to shade in the circle. That will be true. But by the way, it did not say that. What did it say? X is the element of integers, meaning that the fractions cannot be included. When I talk about fractions, Of course, one could argue that 2 over 1 isn't technically a fraction, but I'm talking about a part of a whole, like for example, 1 over 2 or 2 over 5, etc. So can x be negative 1? No. So it's the next value. Remember, x lies between any value in between. X cannot be negative 2 because it does not lie between negative 1 and 2. X cannot be 3 because it does not lie between negative 1 and 2. So the first value x could possibly be 0. So on the line, I'm going to shade 0. X could be 1. Can x be 2? Yes, because we can include the 2 because of this sign here. This symbol means less than or equal to 2. So that is my final answer, right? So what I want us to do now, let's actually, I'm doing one example very quickly because there's quite a lot of examples that we're going to discuss. But let's represent x is a set of negative 1. Okay, let me actually use a new example just so that it doesn't confuse you with this one. Let's represent x is a set of negative 2, let's say it's equal to, and here we have 1, right, where x is the element of real, right, in interval notation. And then after that, we will represent it on the number line, interval notation. So first things first, x is the element of, do we include the negative 2? Yes. So since we include in negative 2, we use square brackets. Square brackets means that we include the amount. Right? So we include negative 2. So x lies between, including negative 2 to positive 1. Can x be 1? No, x cannot be 1 because it's not less than or equal to sign. It's the less than sign. So we use the round brackets. And that is basically how we represent set builders notation. So when we use the round brackets, it means that you're excluding the 1. If it was a square brackets here, it means that you're including the 1. So very quickly, before I move on, let's represent x is the element of including negative 2 to 1, excluding the 1 onto the number line. So we have a number line. We have 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. X, remember x is the element of real, so we can include fractions. X lies between negative 2 and 1. Again, you're using your pencil and ruler. But now, can we include the negative 1? Yes, because we have the square bracket. So I'm going to shade that in. Can we include the 1? No, we cannot include the 1 because we have the round bracket. So we're excluding the 1, so we leave this open. And that is how you represent the value on the number line. Okay. Okay, now let's move on to the exciting algebra part, which is simplification of algebraic expressions, right? Which is very, very fun. Okay, so let's look into it. Right, now, let's say we are required to simplify the following. By the way, I just want to quickly show you something. Now, in grade 9, you looked at FOIL, first, outer, inner, last. So, for example, if I had a plus b times a plus b, the a in the first brackets needs to have a chance to be multiplied to every term in the second bracket, right? Remember in class I did an experiment where I took a tennis ball and one learner who was part of the first binomial, he had a chance to throw it to each learner in the second group. Thereafter, the ball was given to B, positive B in this case, and positive B needed to have a chance to be multiplied to each person in this group. Thereafter, you look for like terms and you had a final algebraic expression, right? But in class, I also showed you that we see a pattern, and whenever we see a pattern in maths, we want to go with it, right? If I have to square binomial, right, instead of using FOIL, which again is perfectly fine, you could use FOIL, I could, this has to do with squaring the binomial, by the way. I could square the first term, a will be a squared. I can multiply the first and second term. A times B is AB. Multiply that product by 2, which many learners tend to forget to multiply the product by 2, which I think is very, very important to note. And lastly, we square the last term, which gives me B squared. Right, great stuff. You do the same thing if I have A minus B all squared, right? You have a binomial, an algebraic expression with two terms, B squared. What is that equal to? That's equal to A squared. You multiply these two together, that gives you negative AB. Multiply that product by 2, which is negative 2AB, and square the last term, which by the way is negative B all squared. Let us forget to include the negative B in brackets, and that means negative B times negative B. You know that a negative times a negative is positive, so that's B squared. Okay, so that was a quick, short cut that we learned. Now let's do an example, which I find very, very interesting. Let's do an example. Right, let's simplify a raised to the power of x, or a exponent x minus 2 all cubed. Okay, this is very, very exciting, right? This is very exciting. At first, you may not know how to deal with this cube, right? Remember, they're not asking you to factorize, they're asking you to simplify, right? So we have to expand. But actually, let's recall the laws of exponents. And I know we're going to look into the laws of exponents in great detail in the next topic. But very quickly, if I can recall from grade 9, grade 8 and grade 9 on our laws of exponents, if I have a squared times a raised to the power of 1, right? I'm multiplying and the bases are the same. So according to the first law of exponents, I keep the common base, which is a, and I add the exponents together, which gives me a cubed. So by that logic, you agree that a cubed is equal to a squared plus, sorry, a cubed is equal to a squared times a raised to the power of 1. Right? Maybe it wasn't too wise of me to use a because we have a in this example, but a is just a variable, right? Of course, we just use it in an example to explain the laws of exponents. So using that logic, imagine that this entire base is, for example, k. So what I'm going to do is I'm going to rewrite this as a raised to the power of x minus 2 all squared times a raised to the power of x minus 2 raised to the power of 1. Okay. Now what we can do here, we can apply the squaring of a binomial. Right? We can apply the squaring of a binomial. It looks very similar to a minus b all squared. So let's follow the same procedure. We're going to square the first term, a. So this is what I have. I have a raised to the power. Let me use a different color, right? So you can see that this is the working out. I have the first term, which is a raised to the power of x all squared. So what law of exponents am I going to apply? And this is why algebra is so interesting, is because we are looking at the laws of exponents before we can do the topic, which we dealt with in grade 8 and grade 9. Now we're going to take it to further power and we're going to multiply it to the exponent. So that is going to give me a raised to the power of 2x. Because remember, x times 2 is 2x. So I have a raised to the power of 2x. Now, how do I get the middle term? I'm going to multiply these two terms together. A raised to the power of x times negative 2 is negative 2 a raised to the power of x. I'm going to multiply the product by 2, which is going to give me minus 4 a raised to the power of x. Then I'm going to square the last term, which is going to be plus 4. Okay, that's being multiplied by a raised to the power of x minus 2. Okay, now this looks complicated, but it's not. It's basically a trinomial being multiplied to a binomial. So every term in this trinomial needs to have a chance to be multiplied to this binomial. Or if it was the other way around, every term in the binomial needs to have a chance to be multiplied by the trinomial. If you want, you can use the commutative property and you can swap this around if you want, right? Again, it does not make a difference. Okay, so I just swapped that around. Okay, now x raised to the power of So a raised to the power of x needs to have a chance to be multiplied to every term in the first term, in the second bracket. So I have a raised to the power of x times a raised to the power of 2x. Using the laws of exponents, I have a raised to the power of x times a raised to the power of 2x. I multiply and the bases are the same. I keep the common base and I add the exponents together. That gives me a raised to the power of 3x. So I have a raised to the power of 3x. Now I have a raised to the power of x times negative 4a raised to the power of x. That's going to give me negative a raised to the power of, remember, a raised to the power of x times a raised to the power of x is a raised to the power of x plus x. X plus x are like terms, so it's going to be a raised to the power of 2x. Very, very interesting. And now I have a raised to the power of x times 4, which is plus a raised to the power of, sorry, a raised to the power of x times 4, which is a raised to the power, so it's 4a raised to the power of x. Okay, good. And now the negative 2, by the way, you take this number as negative 2. Now positive 2 needs to have a chance to be multiplied to each one as well. So just to save some time, I'm going to be a bit quick on this one. Right, so I have negative 2 times a raised to the power of negative 2 times a raised to the power of 2x is negative 2a raised to the power of 2x. Negative 2 times negative 4a raised to the power of x is going to be plus, the negative times the negative is positive, 8a raised to the power of x. And lastly, negative 2 times 4, that's going to be negative 8. Now I look for like terms. Right? Remember, like terms have two properties. They need to have the same variable and they need to have the same exponent. So looking at this example, I can already see my like terms. A raised to the power of 3 cubed. Okay, there's no like term with that. But negative 4a raised to the power of 2x with negative 2a raised to the power of 2x. We can add those two together. So I have a raised to the power of 3x negative 4a raised to the power of 2x minus a raised to the power of 2x is negative 6a raised to the power of 2x. And now I have 4a raised to the power of x plus a raised to the power of x. That's going to give me, what is that, 12. Yes, 12a raised to the power of x. And of course, I have the constant, which is negative 8. Is there any like terms from here? Nope. So this is my final solution, right? And that is how you simplify fractions. Now, factorization is the exact opposite. It's where they give you the expression, maybe it's a binomial or a trinomial or a polynomial, and we have to factorize it. We have to make it a singular term, right, in brackets. We have to factorize fully. That means there shouldn't be a step where we can factorize anymore. We have to factorize fully. So that was, let me just save. Let me just save this before I continue. Okay, let me just. Okay. Save as save. Okay, let me just save this image, right? Okay. Right. Now, that being said, let's look at factorization, which is also an extremely interesting topic. Okay. So, factorization. Right. As I said, this video is just a summary of what we did in class. I cannot go through all the methods of factorization, but I remember once a learner came up to me and said, "Sir, how do we know which method to use when we factorize?" Right? And I said, the first thing you need to do is always take out the highest common factor. Now, granted, in some algebraic expressions, the highest common factor could be 1. So we can't really take out anything, right? If the highest common factor is 1, it wouldn't make a difference to the algebraic expression. Thereafter, we look for another form of factorization. It could be dots difference of two squares, where we have a perfect square minus a perfect square. Or it could be a quadratic trinomial, right? And I can recall, you can use the window method that I showed you in class, or maybe there's also other videos on this channel that you can just take a look at. And I use the window method quite often. There's a grade 11 video that I just posted, and we used the window method as well. We used a k substitution, and then we had k squared, and but basically the equation was in the form of ax squared plus bx plus c is equal to 0, and we used the window method and we substituted, or rather we factorized that quadratic trinomial. Or we could use grouping in pairs, right? Grouping in pairs, usually when you see a polynomial, an algebraic expression with more than 3 terms, that's a good indicator. Now, you could group, listen to this carefully, you could group more than 2 terms, right? So, for example, your final answer could be a plus b plus c and x plus c minus z. That means you could group more than 3 terms. So that's something that I find quite interesting as well when it comes to grouping in pairs, because people, they think pairs, and well, the word pairs, you think about two, and you usually think that there's going to be two in common, but you look for maybe there could be 3 terms in common or 4 terms in common. Very, very interesting. So I cannot emphasize that enough, and that's a good indicator as well. But what I said will always be in the test for a grade 10 test will definitely be factorization of the sum and difference of 2 cubes. Right, now, why do I always emphasize this? Because the other 4 methods of factorization was done in grade 9, right? We looked at this in grade 9. We just recapping and revising and maybe going through more interesting examples in grade 10. But the sum and difference of 2 cubes, this is introduced in grade 10, right? It's not introduced in grade 9. So let's look at an example of this. Oh, before we look at an example, let's see how do we factorize the sum and difference of 2 cubes. Okay, so let's look at the sum of 2 cubes first. Let's say I ask you to factorize a cubed plus b cubed. So I have a perfect cube added to a perfect cube, right? So I think it's quite important that we know our perfect cubes quite well, right? I have a perfect cube added to a perfect cube. Okay, just 1 second. Right, okay. I just wanted to check something, right? So if I have to factorize this, firstly, it will always be a binomial multiplied to a trinomial, right? So it's a binomial multiplied to a trinomial. So you're probably wondering, how do we get the binomial and how do we get the trinomial? So to get the binomial is quite simple. All we need to do is cube root the first term. So if I look at the first term, it's a cubed, so I'm going to cube root the first term. Now the cube root and the cube, they undo each other, they inverse to each other, so I'm left with a. So a will be the first term in my first bracket. Then I'm going to look at the last term, which is b cubed. Right, let's ignore the sign for now, but let's just take b cubed as is. The cube root and the cube, they undo each other, I'm left with b. And I'm adding, so I have plus. Now that's basically a mark. It should be a mark just for the binomial. Now we're going to look at the trinomial. And to get the trinomial, we have to look at the binomial. So to get the first term in the trinomial, I'm going to square the first term in the binomial. So a squared gives me a squared. To get the middle term in the trinomial, I'm going to multiply these 2 terms together. So it's going to be a times b, which is positive ab. Now this is the important part. I need to change the sign. So remember, a times b is positive ab, But now I need to change the sign, so it's going to be minus AB. So again, I cannot emphasize this enough. You need to change the sign for the middle term here. And lastly, we need to square the last term. So positive b squared is going to be plus b squared. And that is how you factorize the sum of two cubes. Now let's look at the difference of two cubes. Right, let's say I ask you to factorize. Usually, by the way, they won't just say factorize. Of course, you have to factorize fully. That means if I look into this brackets, if I can factorize that fully, that's great. If I look at this brackets, if I can factorize that again, I need to factorize using either of the 5 methods of factorization you learned in class, right? But let's say I ask you to factorize a cubed minus b cubed. So now this is the difference of two cubes. Again, the same procedure applies. I have a binomial multiplied to a trinomial. To get the first term, the cube root of a cubed is a, the cube root of b cubed is b. I am subtracting, it's the difference, so there's going to be a minus sign in between. To get the trinomial, I'm going to look at the first term, I'm going to square the first term. To get the middle term, I'm going to say a times negative b. What's a times negative b? It's going to be negative ab, but we need to change the sign. So it's going to be plus ab. Lastly, we need to square the last term. Now, this is where learners get a bit confused. If you look at the last term, what is the last term in this binomial? It's negative b. So I'm going to take negative b all squared, which means negative b times negative b. That gives me b squared. So what will I have in between? I have plus b squared. And that is how you factorize the sum and difference of two cubes. Now, let's look at these two and apply what we learned, right? Let's apply what we learned. So let's look at an example. Right? Let's look at an example. Let's factorize fully. Right? We have x raised to the power of 6 minus 64. Now wait, this does not look like the difference of two cubes. Why? Because we have an exponent of 6. But actually, it is, because remember the laws of exponents. A raised to the power of m or raised to the further power of n is equal to a raised to the power of m times n, right? Okay, let's keep that in mind. What we can do is we can rewrite x raised to the power of 6 as x squared raised to the further power of 3, because 2 times 3 gives you 6, minus 64. Now, actually, this is a perfect cube. If I cube root x squared or cubed, it's going to give me x squared. And if I cube root 64, by the way, we have to make sure that 64 is a perfect cube. It is, because the cube root of 64 is 4. So let's open up our two brackets. We have a binomial multiplied by a trinomial. And let's follow the procedure. First things first, cube root the first term to get the first term in this binomial. So as I mentioned, the cube root of x squared or cubed, the cube root and the cube, they undo each other. I'm left with x squared. So I have x squared. Now, how do we get the second term? The cube root of 64, that is 4, and there's a minus here, so that's minus. Now, how do we get this first term here? We square the first term, right? So we square the first term. I'm going to say x squared all squared. An exponent raised to the further power, it's going to be x raised to the power of 2 times 2. We're applying this law of exponent. It's going to be x raised to the power of 4. Now I'm going to multiply these two terms in the binomial. X squared times negative 4 is negative x squared. Then I'm going to change the sign. Please do not forget to change the sign. It's absolutely important, which is plus 4x squared. And lastly, I'm going to square the last term. So it's negative 4 all squared, which is plus 16. Very, very interesting. Now, as I said, if you can't factorize further, please do so. Right. Let's look at x squared minus 4x. What type of factorization is this? It's dots, difference of two squares. So what I can do is I can factorize this further. I have a perfect square minus a perfect square. So I have two brackets. The square root of x is x. The square root of 4 is 2. And I have plus or minus. Even if you put minus plus, it doesn't really matter. And I have the last term, which is x raised to the power 4 plus 4x squared plus 16. Right? And that is my final answer for that. Okay. Now, what I want to do is, let's look at a couple of other interesting examples. Right? Let's say I have to determine the numerical value of a cubed plus b cubed if a plus b is equal to 5 and a squared minus ab plus b squared is equal to 10. Okay, very, very interesting. Okay, now I want to determine the numerical value of this. First thing I'm going to do is factorize the sum of two cubes. So I have a cubed plus b cubed. I'm going to be quite quick with these two examples I'm going to explain because I want to explain another thing as well. I'm going to factorize the sum of two cubes. So it's going to be a plus b into a squared, change the sign, minus ab plus b squared. But now if I look at a plus b, do I know the numerical value of a plus b? Yes, it's 5. So I'm going to substitute 5 in the place of a plus b, which is going to give me 5 multiplied to. Do I know the numerical value of a squared minus ab plus b squared? Yes, I do, which is 10. So it's going to be 5 times 10, which is 50. Let's do one more example on determining the numerical value when given these expressions, and certain expressions have numerical values to them, right? So let's look at the next example. Let's look at example 2 with regards to determining the numerical value. So let's say we have to determine the numerical value of, right? Let's say we have to determine the numerical value of a cubed minus 1 over a cubed if a minus 1 over a is equal to 2 and a squared plus 1 over a squared is equal to 5, right? So the first thing I'm going to do, I want to determine the numerical value of this expression. So let's start off with this expression, a cubed minus 1 over a cubed. You might not realize this, but this is actually the difference of two cubes. So step number 1, let's factorize the difference of two cubes. Let's factorize this expression, right? So I have a binomial multiplied to a trinomial. How do I get the first term here? I cube root a cubed, which gives me a. By the way, what's the cube root of 1 over a cubed? It'll be equal to the cube root of 1 over the cube root of a cubed, which will be 1 over a. So it's 1 over a. And of course, I have a minus sign in between. Now, how do I get the trinomial? I look at the binomial. Let's look at the first term in the binomial. A squared is a squared. Let's multiply these two terms and then change the sign. So let's multiply those two together. Let's say we have a multiplied to, remember it's a over 1 multiplied to negative 1 over a. How do we multiply two fractions, by the way? Top at the top, bottom at the bottom. So it's going to be negative a over a. The a's divide off. I'm left with negative 1. And we need to change the sign, so it's going to be plus 1. And lastly, let's square the last term here. Negative 1 over a all squared is positive 1 over a squared. Now, using the commutative property, because the commutative property allows us to swap numbers around, especially when we add in or multiply. Let's take this first term in this trinomial and swap places with this term. So we're just going to change, not swap places, but make it next to that term. So what do we have? We have a minus 1 over a squared plus 1 over a squared plus 1. Right? So do we know the numerical value of a minus 1 over a? Yes, we do. It is 2. So we have 2 multiplied 2. And do we know the numerical value of these two terms? A squared plus 1 over a squared. Yes, we do. It's 5. So it's going to be 5. And of course, we have this 1 here. Please do not forget about this 1. It's extremely, extremely important. So I need to add that 1. So I have 2 times 6, which is equal to 12. So the numerical value of a cubed minus 1 over a cubed is 12. Now, again, I cannot go through all the examples in your textbook. It's up to you to revise. Please go over factorization of the quadratic trinomial. If it involves fractions, it's quite important. Please go over the difference of two squares. Please go over taking or removing the highest common factors, and always trying to see if you can factorize even further. I think that is extremely important. Okay, grade 10s, I wish you all the best and enjoy the rest of your day.